All right, so this is, I think, the last part of abstract data structures. I think, maybe. And this is where we talk about dynamic data structures in a general sense and why we would use particular data structures over other ones. So really answering those bigger questions of, okay, I know what a linked list is, I know what a stack is, I know what a queue is, but why am I going to use these particular data structures in these particular situations? So we have talked about these abstract data structures: stacks, queues, linked lists, and binary trees. And when we're drawing the line between static and dynamic data structures, the key feature of dynamic data structures is that they can change size during execution of a program, and specifically that they can grow and shrink. So they can take up more or less memory. It is determined during the processing of the program and not beforehand. And ultimately, that makes them a very efficient use of memory space when they are used appropriately. So this is why I asked the bell work that I did about comparing the use of static and dynamic data structures. This is actually, once you understand how to read it, this is a great way of understanding the differences in not only what dynamic and static data structures are, but the difference is in when you would use them and why you wouldn't use them. So dynamic data structures, as I just said, can change in size while the program is running. Static data structures do not change in size. They are the size that they are. Think a list or an array. That you say, okay, this list is 100 items long, and that's it. In Python, a list is actually a dynamic data structure. It can change in size while the program is running. Python essentially uses a linked list for its array. You can make a static array in Python. You would have to declare its size immediately. So you would say like list equals, for example, list equals 100, something like this. I forget. There is, I don't know that that's the notation, but that's the notation in some programming languages where you say, it might even be like this. Where you're declaring it to have a particular size. But Python, by default, keeps those dynamic. So there are advantages to dynamic data structures. As we just said, only uses the space needed at any time. It makes an efficient use of memory. And ultimately, the storage that's no longer required can be returned to the system for other use. What that means is that RAM, now that we understand the underpinnings of the computer, that RAM, that memory, can actually be given back to the system. And so it can be like, hey, I don't need this memory anymore. Use it for something else. And so programs can grow and shrink the entire memory footprint that they're using when they're using dynamic data structures. A disadvantage to dynamic data structures, as you've seen, is that they can be more difficult to program. Right? Where you're struggling with linked lists right now, and you know, it's the first time you've seen linked lists. Everyone struggles with figuring out how does this work, and how do I connect this node to the next one. They require more work in order to program them. In order to search, you might be able to imagine that it's going to be slow. I've got to go from node to node to node to node in order to search through this thing. But that's not always the case. It depends on how you actually write your dynamic data structure. And specifically for a linked list, it only allows you to search serially, which means one by one. So if you start at the head, you have to go one by one to see if you've hit the one that you want. And if you start at the tail, you know, if it's a doubly linked list, you can go back towards the beginning. but still, it only allows one-by-one search. Okay, static data structures. Doesn't change in size. During compilation, when the program is compiled, when the program is put together, the computer allocates space. It says, all right, the advantage is that we have exactly this much memory. This much memory cannot be used by anything else. It can only be used by this array or static data structure. They're easy to program because computer programming languages, they have them right in the language itself. It's just like, it's right there. It's easy to program. It's easy to check for what's called overflow. Overflow is when you have too much memory or too much data to put into the memory. So if you have a list that is 100 items long, it's a static data structure, it's only 100 items long, and you try to put that 101st item in there, your computer program can very easily check to see that that's an error and stop it from happening in the first place. Whereas over here, if you have a linked list and you try to put that 101st element in and there's only enough memory for 100, then it's very difficult for the computer program to detect that it's having a memory issue, all right? So an array allows for random access, meaning that I can go and get the 61st element, and I can get the 3rd element, and I can get the 25th element. And it doesn't matter that I've seen the previous ones. I can just go get whatever element I need. As far as crashing, that is a very realistic problem. That is something that happens when you try to either use memory that you don't have, or you try to reference a piece of memory or a piece of data that doesn't exist anymore because it got overwritten, or you get in an infinite loop because of some memory issue. So yes, crashing is something that, or a program that hangs, and that is something that often happens with poorly programmed dynamic data structures. A disadvantage of static data structures, and even though it looks like this one should be attached to advantages, it's a disadvantage. The programmer has to estimate the maximum amount of space needed. So that means that if you're not sure how much space something's going to need, you have to always edge towards the maximum. You always have to bump your estimate up. So if you think, yeah, it might use 500, 600, maybe 700 elements, you have to go, well, 700 is what I think is a maximum, but to be safe, maybe I want to go to 1,000. And 1,000 might take up a lot of memory. So that is a disadvantage. And sometimes it can be difficult to estimate. And the other thing is that it can waste space. If I allocate 1,000 elements to this array, to this list, and I only use 10 because this particular iteration of the program only used 10 out of that 100, well, those other 990 elements are just wasted memory. There's no data in there, and no other program or no other part of the program can use that memory because it's been allocated. The operating system itself says, no, you cannot use that. That memory has been reserved for this program, for this list, and nothing else can use it. So that is a problem. Before I move on, any other questions about static or dynamic data structures? Okay. So, a suitable structure for a given situation. This is easily the most important part of like abstract and abstract data types. So, understanding why we would use these things. All right, stacks. And this might not make sense right now, but hopefully through examples it will. The most important application of stacks is to implement function calls. All right, remember that stacks are first in, last out. So what it means is that if there's a function within a function within a function within a function, the last one called is the first one that the operating system needs to call, needs to implement, needs to run. After it's done with that, then it can call the next one. And then after it's done with that, it can call the next one, and the next one, and the next one. The last one it calls is the first one. So if I have a function that says, let's say add together the product of two numbers. That's that first function on the bottom of the stack. Well, within that function of adding together the product of two numbers, there's going to be a function call that says multiply, because I need to get the product of those two numbers. And then within that multiply function, maybe there's a function that says round those numbers off. And so that rounding function is the first one that's going to be called. It's going to round before it does anything else. Because if it tries to add, if it does that first function first, then it's going to be adding up nonsense, right? So it's got to do the last function first. That's first in, last out, right? It's also last in, first out. So does the rounding, and the result of that rounding gets used in this multiplication. And then the result of the multiplication gets used in the addition. And then the addition can happen. All right, so stacks are really important for how a computer program actually gets executed, because it's got to be that last one that happens first. Most compilers implement these function calls by using a stack, and it provides a technique for eliminating recursion. Instead of calling the function recursively, the programmer uses a stack to simulate the function calls in the same way that the compiler would have done so. That's a more advanced way of thinking about a stack. Really, I want you thinking about a stack as a way of the computer saying, this last thing that the user told me to do in this computer program is the first thing I need to execute, all right? But instead, and don't get confused with the two uses of recursion here, instead of doing a stack, you can simply write a recursive function that essentially does things as a stack. So your Fibonacci program essentially did a stack, because what it did is it said, all right, let's find the 10th Fibonacci number. That 10th Fibonacci number said, add up the 9th and the 8th Fibonacci numbers. But the 9th Fibonacci number said, okay, add up the 8th and the 7th Fibonacci numbers. And the 8th said, add up the 7th and the 6th. And the 7th said, add up the 6th and the 5th, and so on and so forth. And it keeps on going up and up and up and up until we get to add up, or what is the first Fibonacci number? And the first Fibonacci number you defined. And you also defined the second Fibonacci number. So once it got up here to add the first and add the second, then it had a return value. And that first ended up being the return value for the second. The second plus the first ended up being the return value for the third. The third plus the second ended up being the return value for the fourth, and so on down the line until you got to that first function call of what is the 10th number in the Fibonacci sequence. So recursion is the main way that you can think of stacks. If you think that way, you can also just think It's going to be that last thing I ask the computer to do that it's going to execute first. After it does that last thing, then it'll do the second to last thing, and then so on down the stack. Questions about stacks? Awesome. Okay, so queues. We know queues in real life are like getting in line at the bank, getting in line for lunch. We know that it's the first one in, first one out. But in computers, queues are used for serving requests of a single shared resource, like a printer. You know that if you're the first one to print to that printer, then your printout is going to be the first one that gets printed. You know, if you get in line last, I know this as a teacher, I want to get in early in the morning so that I can get my stuff printed out. If it worked like a stack, that would just be backwards, and I would be mad, because that would mean the last person to try to print something out would end up going first, and that doesn't make any sense. And so should always be the first person to request that resource ends up being the one who gets that resource. The same thing works internally in the computer. The first application to ask for disk space gets that disk space. The other ones have to get in the line. The first application to ask for CPU time in order to process some calculation gets that CPU time. The other ones have to get in the line. This is obviously a little outdated, but your phone works on the same idea, that if you are trying to stream a video on your phone or on your computer, there's going to be a buffer, a waiting line. There's going to be some seconds of that video that are going to be waiting in order for the first seconds to be broadcast. And then those second seconds will come along and be broadcast. You can think of it as a playlist for a jukebox. Someone says, hey, I want to play this song, or just a general playlist. I'm going to add songs to the end of that playlist. And as the song gets played, it comes off the queue, the next one comes up. Another internal computational piece of queues is interrupt handling. So remember, interrupts are things that happen from inputs, that happen from the keyboard, from the mouse, from the microphone, from the camera, Bluetooth. All of these things have to happen in a particular order. If I try to click on something and then type, it's very inconvenient if the typing happens before the clicking, because then I'll be typing in the wrong place. So the interrupts, the handling of those interrupts have to happen in a queue order, first in, first out. Otherwise, it'll cause unexpected behavior, and the software won't behave, the computer won't behave the way that I think I'm interacting with it. If I try to swipe and then tap, if that interprets it as a tap and then a swipe, then my phone will not be behaving the way I expect it to. Questions about queues? Great. Okay, linked lists. Let's keep in mind for linked lists that Python lists are implemented as linked lists. And so when you're making a Python list, you don't have to tell it ahead of time how many elements are in that list. You can make it however as big or small as you need it to be. Now, Python does allow random access to elements. It does that by actually going through and searching for item number 35. If you say, I want to get item number 35 off of my list, you go list, square brackets, 35. Python makes it look like you're getting random access to that element, but what you're actually doing is you're starting at the beginning and going to element 35. It's actually really inefficient the way that Python ends up doing it for a really big list. And this is why when you're programming in Python, if you have a really big list, you'll notice that it's super slow. So in Python, if we want to actually have really big lists of lots of information, then we need to start doing statically typed data structures. But as long as you don't need random access, you can hold a lot of data in a linked list. All right. So basically, if you don't need to have that random access, if you don't need to get to element 35 or element 5, then a linked list can be the way to go. Especially if you want to be able to insert items in the middle of the list. So a reason that you would do this is like a priority queue. For example, if, let's go back to the printer. Mr. Kim, me, Ms. Schneider, and Ms. Williams are all trying to print things. Well, Mr. Kim, he gets priority, right? He's principal. His stuff should always get printed first. So if you want to have a linked list of items to be printed out, that this would be a way to implement what's called a priority queue. And you could say, okay, when Mr. Kim prints something out, then he always, wherever the list is, he's always going to be like second, no matter how long the list is. And if there's no list, then he's first. But otherwise, then he'll always be second. And that'll make sure that the current job gets printed out and then his job gets printed out. And so that would be a priority queue. And in fact, linked lists are often used to make queues. They're often a way to do a queue. And what you do is you always add an incoming item to the head and you take the outgoing item from the tail. You can also flip-flop it, but having that tail pointer and the head pointer allows you to actually make a very efficient queue from a linked list. I think the thing to remember about linked lists is you use it when you want to have a list of things, but you don't need random access and you want it to be efficient. And the other piece is when you don't know how many items are going to be in the list. And you might have a really small one and you might have a really big one. And so this is very common in programming. This is why Python's default list is a linked list. Calling an element from the list is inefficient, but in a Python list. If you use some other what are called strongly typed programming languages like C++ or Java, you have to say my array is exactly 1,000 items long, and then it's very efficient pulling that one item out. But with a linked list, it is very inefficient because it operates in O(n) time versus O(1) time. Big O of n, because if you have 1,000 items, you potentially have to go through 1,000 items just to get to your item. Versus a statically typed array, which you have random access, and so that's big O of 1, because if I want to get to the 47th element, I'm just going to one element and getting what I need. So a linked list has inefficient retrieval unless you're getting it from the head or the tail. Are we good to the linked list? Cool. And arrays. So arrays, remember, are the static ones. Again, that's when you want random access to elements. You want to be able to get the 47th one out. You want to get the 93rd one out. When we did the forest ecosystem model, I think the best one was to actually have arrays. Even though we used lists, we used linked lists, the best one was probably to use arrays, because we wanted to be able to say, all right, reproduce this one with this one and make an offspring. We did a little bit, I think we did a little bit of the game of life, That is another one where you need random access to elements. It's best, of course, when you know the elements, the number of elements ahead of time. But if you know that you're going to fill up all of the elements of the array, it will take up less memory than a linked list. But if you're not sure if you're going to fill up all the elements of the array, then you have to make a decision between a linked list and an array. All right. So just understanding this fundamental difference between a linked list and array is the most important part here. Finally, binary trees. There are lots of different kinds of binary trees, and we are not going into great detail for these because they get pretty complicated pretty quickly. And so there's something called a binary search tree, which I mentioned earlier in the year. And what it is, it's a sorted binary tree, so that if you go left, you're going in a decreasing way. So if you go left, you're going down in the list. And if you go right, you're going up in the list. So if I'm looking for a particular number in a binary search tree, if I'm looking for 35, and the head node of the binary search tree, the root node, is 50, then I know I need to go left because I need to find something that's less than 50. The next node I end up at is 25. I know I need to go right. I also know, because how a binary search tree works, is that everything that's to the right of 25, that is to the left of 50, is going to be between 25 and 50. It's already sorted. Binary search tree is something that has to be already sorted. So maybe I end up at 36. Oh, 36 is too much, so let me go back to the left. Maybe then I find 35. Well, that took me 1, 2, 3, 4 hops to get to 35. All right, and that can be a very efficient way of storing sorted data. And it can be very efficient because how I add more data is also really easy. If I know I need to add 24, I start at 50, I go to 25, I'm like, well, let me go down to the next one. All right. Are there any child nodes off of 25? Oh, there's a child node here of 12. Are there any child nodes off of 12? They're not. Oh, well, I know that 24 needs to go to the right of 12. And so it's really easy to insert nodes in a binary search tree as well, because I know exactly where that needs to end up. So binary search trees can be really helpful, really useful for all sorts of different applications, maintaining a sorted list. Heaps, I'll let you read about that. They're really cool data structures. Understand that they are an implementation of a binary tree. I'm unfamiliar with GGM and syntax trees. Actually, I have done a syntax tree before, I lied. I am somewhat familiar with syntax trees. GGM trees I have never worked with, and that's cool that they generate a tree of pseudo-random numbers. That is an application. Syntax trees are ways to parse computer programs and then determine what actual functions should be called from those computer programs. So that's very much like internal workings of a computer. The one implementation of a binary tree that you should be familiar with is the binary search tree. And there are really great resources about how those work. No, the GGM and syntax trees are not important for you. Heaps, the only important thing is just to be familiar with the fact that they are a type of binary tree. That's it. You don't actually need to know what they're really used for. Binary search trees, you need to know a little bit more detail. if you understood what I said, then you're all set. But that's about it. Binary search trees are really the most often used form of a binary tree. This is a fun flowchart for trying to determine what data structure to use to hold your particular data. So we see here, if we have one data item, then, and if we want letters, then we use a character. In Python, it's just a string. All right, it doesn't matter whether we have single letters or multiple letters, we still just use a string. If we have a number, then we want to see if it has decimals. If it does have decimals, then we should use a double or a float. Python has floats. If it doesn't have decimals, then we use an integer. And that's how we determine what kind of data structure we need. Then if we have multiple data items, we need to determine, is order important? If order is important, we need to determine whether we want to implement it FIFO or LIFO. So first in, first out, or last in, first out. That helps us determine between queue and stack. And then if order is not important, but we need to know how many elements there are. If we do know how many elements there are, then we're going to use an array. If we don't, then use a list. This is a really simplified version of how do I know what data structure to use. If you want to implement a queue, then a linked list is a really good way to implement that queue. You can also implement a queue with, implement a stack with a linked list. You wouldn't need a tail pointer, you would just need a head pointer. And you just add one to the head pointer every time. And then when you're ready to peel things off, you just peel it off from the head pointer. You don't need to actually have a tail pointer for a linked list version of a stack. And then a binary tree could be used to implement a queue as well. Or if you needed your list to be sorted. Okay, so they interact in different ways. It's not like you're choosing between a binary tree and a queue. It's not like you're choosing between a linked list and a stack. And finally, this is a way of visualizing the relationships between these different data structures. So yet another way of thinking about these abstract versus static data structures. Any questions? All right. Let's take a look at that linked list project then.